are looking here at the surface burst of a nuclear explosion. The nuclear weapon, already used with devastating effect against cities and civilian population, may be encountered on any battlefield of the future, where its principal effects will be much lessened against troops trained to take correct precautions. Let us summarize the main characteristics. There is flash, which can be sensed by the eyes, even when shut and shielded. There is heat radiation, which can be felt on the skin. There is shock wave or blast. Close to the burst, this is felt and heard as a sharp crack, similar to the noise of a field gun. At a distance, the effect is that of a sustained loud rumble of thunder. There is another element new to warfare, nuclear radiations. These will be described more fully later. For the moment, note that nuclear radiations cannot be detected by any of the human senses. Their presence and intensity can only be detected by sensitive instruments. Finally, there is the characteristic visible feature of the ball of fire and the mushroom cloud. The energy released by nuclear weapons is measured in terms of that produced by a given quantity of TNT, a typical high explosive. Thus, a 1 kiloton weapon, abbreviated to 1 KT, yields the energy of 1,000 tons of TNT, sufficient to cover an entire football pitch with HE shells. Similarly, a 10 kiloton weapon is equivalent to 10,000 tons of TNT, enough to cover 10 football pitches. And so on up to 1,000,000 tons of TNT, where the nuclear prefix changes to mega, as in a 1 megaton weapon, abbreviated to 1 MT. Nuclear weapons can be delivered on the target by air, by artillery, by guided weapons, rockets, or mines. A nuclear weapon can be exploded in the air, in which case the fireball does not touch the ground. The point on the ground directly below the burst is known as the ground zero, or GZ. Or the weapon can be exploded as a surface burst, where the fireball touches the ground. Here, the actual point of burst is the ground zero. Or it can be a subsurface explosion. Here, the point on the ground directly above the burst is the ground zero. The initial flash of light, the heat radiation, the shock wave or blast, and the immediate nuclear radiations are known as the immediate effects. These are virtually completed in times varying from a few seconds to a few minutes, depending on the size of the weapon. For most weapons, the duration can be taken as 1 minute. We will examine these characteristics in more detail. The intense flash of light from a nuclear explosion is many times brighter than the noonday sun, and may cause temporary blindness for a period ranging from a matter of seconds by day to some minutes by night. If any attempt is made to look directly at the fireball during the early stages of the explosion, especially by night, permanent damage to the eyes may result. The flash of light is accompanied by the radiated heat. This travels mostly in straight lines at the speed of light and is similar to the heat radiated from the sun. Some of it, however, will be deflected or scattered by particles in the air, or reflected from the surface of objects it strikes, and so to a limited extent it may reach round corners. The pulse of radiated heat from a 20 kiloton weapon lasts for about 1 second, most of the immediate effects being radiated in the first half second. From a 10 megaton weapon, the radiated heat persists for about 20 seconds, being mostly dissipated in the first 10 seconds. In spite of the relatively short duration of the radiated heat, its intensity is sufficient to cause burns on bare skin exposed even at a considerable distance from the point of burst. The severity of the burn depends upon the distance from the explosion, the length of time for which the skin is exposed, and upon the area of the body's surface burnt. Combustible material and equipment may be charred or set on fire. Trees, undergrowth, soft-skinned vehicles and canvas covers, camouflage nets and woodwork. The effect of the radiated heat may be reduced by dense industrial haze or cloud by as much as 1/2 when the burst takes place above it. But should the burst occur below it, much of the radiated heat may be reflected back to the ground with increased effect. Next, shock wave or blast. As the fireball expands, a shock wave develops, commonly referred to as blast. As this hits the ground, it is reflected back. Since the reflected wave is traveling through air already heated and compressed by the direct wave, the reflected wave travels faster, catches up with the direct wave, and reinforces it. The two waves join together to form the shock front with an increased pressure, and hence with a greatly increased range of damage. The shock wave travels at approximately the speed of sound, 1100 feet per second. The initial shock wave from a nuclear explosion lasts much longer than an HE explosion, and hence the effects are different. An HE explosion shatters buildings by striking a sharp, hard blow. A nuclear explosion delivers an initial hard blow followed by a prolonged push. This either flattens a building or leaves it leaning away from the direction of the blast. Let us examine the changes in pressure with time at any one stage, remembering that the heat radiation comes first and is almost instantaneous. For a short interval after detonation, there will be no increase in pressure, since it takes time for the shock front to travel from the point of explosion. On arrival of the shock front, the pressure will increase suddenly to a large value. This is the positive or compression phase of the blast wave. For a 20 kiloton explosion, it lasts for roughly 1/2 to 1 second. And for a 1 megaton explosion, for about 2 to 4 seconds. This positive phase is the period of maximum destruction. After this, the pressure falls again until it is the same as that of the original atmosphere. Next, the pressure falls to below that of the original atmosphere. At this point, the wind caused by the blast blows back towards the point of explosion and may cause further damage, although pressures and speeds experienced are lower than those of the positive phase. This period is known as the negative or suction phase. It lasts longer than the positive phase. For a 20 kiloton explosion, from 1 to 2 seconds. For a 1 megaton explosion, from 4 to 8 seconds. Eventually, the negative blast wave pressure rises again to that of the original atmosphere, completing the immediate effects of heat and blast. Blast from an airburst nuclear explosion creates the greatest range of damage to material. But for any particular yield weapon, there is an optimum height of burst, depending upon the type of target attacked. If the burst is too high, the increased distance between it and the ground zero results in the dissipation of much of the destructiveness of the reflected waves. If the burst is too low, much of the blast energy is expended in forming a crater or in causing damage heavier than is necessary at the ground zero and around it. Similarly, there is an optimum height for the maximum effect of heat and for the maximum radiation effects, again depending on the type of target. Next, we come to nuclear radiation. The four main types of radiation produced by a nuclear explosion are alpha particles, shown here in red, beta particles, shown in blue, gamma rays, green, and neutrons, white. First, alpha particles. Those produced with the immediate effects are all absorbed in the fireball and present no immediate danger to human life. Those produced from residual effects may become a hazard. Alpha particles travel only a few inches in air. And can be stopped by a sheet of paper, by clothing, or by the human skin. They may, however, become a hazard if agents emitting alpha particles penetrate into the body through abrasions or wounds, or if they are swallowed. Next, beta particles. These can travel only a few feet in air. Most of them can be stopped by a thin sheet of metal. They become, however, a source of danger to the skin if beta-emitting agents lodge on the body and are allowed to remain there. The symptoms appear as a reddening or a blistering of the skin. This may not become apparent until some time after exposure. Again, serious injury may result if beta-emitting particles gain access to the body through wounds or abrasions, or if they are swallowed. Gamma rays are of energy similar to, but much more powerful than X-rays. Like these and like wireless waves, they can travel considerable distances and can penetrate the human body, buildings, and other materials. In so doing, they become reduced in strength according to the density of the substance through which they pass. The best protection is offered by lead. For example, a 2-inch thick sheet of lead gives a reduction factor of 10. As compared with steel, where 4.5 inches of thickness are required to give the same reduction factor of 10. Other examples giving a reduction factor of 10 are concrete, 18 inches, rammed earth or brick, 24 inches, and loose earth 36 inches. Neutrons, basic particles of all matter, travel a shorter distance in the air than gamma rays. But they can penetrate many steel, for example. Light elements, such as the hydrogen contained in water, tend to absorb neutrons better than heavy materials. But since gamma rays are produced by this process, heavy materials are required as well to stop the gamma radiations. A shield against neutrons should therefore contain both light and dense materials. Wet earth and concrete are good shielding materials against neutrons and against nuclear radiations in general. If the air burst is sufficiently low, neutrons have the power to induce radioactivity in other substances, such as the ground and materials in the vicinity of the ground zero. This cannot be removed by decontamination. It must be left to decay naturally over a period of time. Nuclear radiations travel mostly in straight lines, but they can be deflected by collisions with particles in the atmosphere, much after the fashion of billiard balls. This property of scatter enables nuclear radiations to reach round corners and into the bottom of trenches. For convenience in nuclear defense, radiations are divided into immediate and residual. Immediate radiations are those emitted during the period of the fireball, for a period of a few seconds to a few minutes, depending upon the yield of the weapon. Residual radiation is radiation from land, water, material or objects contaminated by neutron-induced radioactivity, or by radioactive dust or rain in the form of fallout from the sky, persisting after the immediate effects are over. The penetrating power of immediate radiation is greater than that of the residual radiation. With immediate radiation, for example, a reduction factor of 10 is provided by 18 inches of concrete. With residual radiation, the same reduction factor of 10 can be obtained by only 9 inches of concrete. Although the human body is accustomed to a certain amount of nuclear radiation daily in the form of cosmic radiation from outer space and radiations from other sources such as luminous wristwatches, medical X-ray apparatus, etc., all nuclear radiations must be regarded as potentially dangerous. Any dose has a harmful effect on the human body. A large dose produces radiation sickness. A very large dose will cause death. Remember, residual radiation cannot be destroyed. It must be left to decay with the passage of time. Note also that there is negligible residual radioactivity from an airburst nuclear explosion, since the radioactive particles contained in the mushroom cloud will be carried so high and dispersed so widely that they will have decayed to a harmless level by the time they reach the ground. We can now consider the characteristics of the various types of burst. First, the air burst. Here there is flash, heat radiation, shock wave or blast, and in this case, nuclear radiation, immediate only. Next, the surface or near surface burst. Here again there is flash, heat radiation, shock wave or blast, and in this case nuclear radiations both immediate and residual. A shallow crater will be formed, which with its immediate surroundings will be highly radioactive. Next, the underground or subsurface burst. Here there may or may not be an initial flash. Most of the initial heat radiation will be absorbed by the ground. There is a heavy ground shock similar to that of an earthquake, but the blast effect is much reduced. The immediate nuclear radiation is mostly absorbed in the ground. A vast quantity of debris and dust is hurled into the air, leaving a deep crater. The larger portions of the debris then start to fall back, forming a distinct lip round the crater. Meanwhile, a highly radioactive dust cloud is formed. This moves outwards from the explosion. A large proportion of the dust and debris is sucked up into the air with the nuclear cloud, eventually returning to the ground as radioactive fallout. The residual hazard is very considerable, both from induced radioactivity and from fallout. An underwater burst differs considerably from any other type of nuclear explosion. There is no flash. Most of the heat and the immediate nuclear radiation is absorbed by the water. A shock wave is produced in the water. This can damage ships both above and below their waterline. Vast masses of water are thrown up into the air, and as they fall back, a dense cloud or mist of water droplets forms at the base of the upthrown column. This highly radioactive cloud, known as the base surge, moves rapidly outwards from the explosion area and rises gradually until it merges with the other clouds in the sky. From this cloud, radioactive water may fall as rain, whilst the hot gases are vented through the center of the water spout to form the characteristic cauliflower cloud. Residual radiation is not a major hazard in water, since it is soon dissipated, but it may create a considerable hazard to ships or to shore installations contaminated by the base surge or by the radioactive fallout, particularly if the explosion has thrown up radioactive mud or debris from the sea floor. You have now seen the hazards with which you may be faced: the flash, the heat radiation, the shock wave, and the nuclear radiations. Your training will teach you the immediate actions to be taken in an emergency. If you know the threats and are alert to combat them at a second's notice, your survival and that of your comrades is all the more assured.